Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this solved exercise, we are going to draw the oscilloscope connections required to measure the voltage in the circuit. Determine the differential equation that governs the variation of the voltage across a capacitor fed by a constant voltage. Determine the expression of the time constant. Determine the value of the capacitance of the capacitor and the resistance of the circuit. Determine the average power delivered by the battery during the charging process.
In the shown circuit, a capacitor of capacitance C, a resistor of resistance R equal 90 ohm, and a switch K are connected across an ideal battery of electromotive force E equal UAD. We press the I and V button on the oscilloscope, and we close the switch K at time 0. Part 1.1. Specify what does each channel of the oscilloscope display. The ground of the oscilloscope is connected to point F, and since the phase of channel 1 is connected to point A, then channel 1 displays the voltage UAF across the resistor. And since the phase of channel 2 is connected to point B and the I and V button is pressed on the oscilloscope, then Y2 or channel 2 displays the voltage UFB across the capacitor.
Part 1.2. Indicate the direction of the charge current. Look at the circuit. The current flows out from the positive pole of the battery. Then the current in the circuit is clockwise. Part 2.1. Determine the differential equation that governs the variation of UC, which is taken as UFB. Let's apply Kirchhoff's voltage law. So we have UAD is equal to UAF plus UFB plus UBD. UAD is equal to E, UAF is equal to plus Ri because the positive sense is from A to F through the resistor of resistance R. UFB is taken as UC and UBD is equal to 0 because it is the voltage across a closed switch. Now, look at the positive sense. It enters the capacitor through the plate of charge Q, then I is equal to plus dQ by dt, but Q is equal to CUFB, which is equal to CUC. This is going to be C duc by dt. Replace I in the above equation by C duc by dt, and finally divide the equation by RC. So we have duc by dt plus uc over rc is equal to E over rc. This is the differential equation that governs the variation of uc.
Part 2.2. The solution of the obtained differential equation is uc equal A into 1 minus e to the power minus t over tau, where A and tau are constants. Determine the expressions of A and tau in terms of ER and C. UC equal A into 1 minus exponential minus t over tau. Expand, so UC becomes A minus A exponential minus t over tau. Now let's differentiate UC with respect to time. A is constant, so the derivative of A with respect to time is 0. Now let's differentiate minus A exponential minus t over tau. Minus A is constant multiplied by variable, so the derivative of this term is minus A into the derivative of e to the power minus t over tau. But the derivative of e to the power minus t over tau is equal to minus 1 over tau into e to the power minus t over tau. So duc by dt becomes a over tau exponential minus t over tau. Now replace duc by dt and uc in this differential equation. A over tau e to the power minus t over tau is equal to duc by dt. A minus A exponential minus t over tau is equal to uc. We get this equation. Now multiply 1 over rc by A minus A exponential minus t over tau. We get this new equation. We observe that A exponential minus t over tau is common in these two terms. So let's take a exponential minus t over tau as a common factor. We get this new equation. Now, this equation, or the right side of this equation, is constant. So to have a solution, the left side of this equation must be constant. But a over rc is also constant. Then the first term of this equation is constant only when 1 over tau minus 1 over rc is equal to 0, because a exponential minus t over tau is variable. Therefore, a over rc is equal to e over rc. We can conclude that a is equal to e. And since 1 over tau minus 1 over c, 1 over rc is equal to 0, so we can conclude that tau is equal to rc.
Focus, please. This is important.
Let's move to part 3. Look at the graph. The vertical axis represents voltage in volts. The horizontal axis represents time in seconds. We have two curves, the curve of UC versus time and the curve of the voltage across the resistor UAF, which is taken as UR versus time. We want to use the graph to answer the following questions. Question 3.1. Prove that the capacitor is initially uncharged. Look at time 0 on the graph. At time 0, UC is equal to 0, which means that the capacitor is initially uncharged. Question 3.2. Determine the value of the time constant tau. We know that at time tau, the capacitor completes 63% of the charging process. So, 0.63 times UC max, which is the maximum voltage across the capacitor, is equal to 0.63 times 8, and the answer is 5.04 volts. Look at the curve of UC. The maximum value of UC is 8 volts. Now, 63% of 8 volts is equal to approximately 5 volts. So, on the graph, when the voltage across the capacitor is 5 volts, the time is 0.36 seconds, which means that tau is equal to 0.36 seconds. Finally, we want to deduce the value of the capacitance C of the capacitor. We know that tau is equal to R times C, so C is equal to tau over R. Tau is equal to 0.36 seconds and capital R is equal to 90 ohms, and the answer is 4 times 10 to the power minus 3 farads or 4 millifarads.
Part 5. Prove that you are equal e exponential minus t over tau, and then refer to the graph to deduce the value of e. We have e equal ur plus uc, proved in number 2.1. Rearrange, then ur equal e minus uc, but uc is equal to e minus e exponential minus t over tau. Now replace uc by its expression, so ur becomes e minus e plus e exponential minus t over tau. E minus e becomes 0, so ur is equal to e exponential minus t over tau. Also, we have another method to prove the expression of ur. We have ur is equal to I times r, but I is equal to c duc by dt, and duc by dt is equal to e over tau exponential minus t over tau, and tau is equal to rc, so rc over tau becomes 1. Therefore, ur again is equal to e exponential minus t over tau. Now, let's determine the value of e. Look at the graph. At t equals 0, ur is equal to 8 volt. Now, replace t equals 0 and ur equal 8 in the expression of ur. So, 8 equal e to the power 0. E to the power 0 is equal to 1. Therefore, e is equal to 8 volt.
Let's move to part 6. Calculate the time delta t needed by the capacitor to practically become fully charged. This time is equal to 5 tau. Tau is equal to 0.36 seconds. Then delta t is equal to 1.8 seconds. Part 7. During the time delta T, the electric energy WR consumed by the resistor is equal to the electric energy WC stored in the capacitor. So we want to determine the total energy delivered by the battery during the time delta T. During the charging process, we know that the battery supplies electrical energy to the capacitor and to the resistor, which means that the total energy supplied by the battery is equal to WR plus WC, but WR is equal to WC. So we will replace WR by WC. This is going to be 2WC, and WC is equal to 1/2 CE squared. Replace C by 4 times 10 to the power minus 3 farads and E by 8 volts. The answer is 0.256 joules. Part 7.2. Deduce the average power delivered by the battery during the time delta T. The average power delivered by the battery represents the rate at which electrical energy is supplied by the battery to the circuit. The average power is given by this expression, W total divided by delta T. W total is equal to 0.256 joules and delta T is 1.8 seconds, and the answer is 0.142 watts.
Thank you for watching. If you like this video,
subscribe to the channel, hit the like button and share.